Hello everyone. On behalf of Indian National Trust for Art and Cultural Heritage, INTACH and the INTACH Conservation Institutes, it gives me great pleasure to welcome our distinguished speaker David Thickett and everyone who has joined us for today's talk in the Conservation Insights 2020 lecture series. I'm Dr. Padma Rohela, Director ICI Delhi. Now to introduce our speaker, David Thickett has a degree in natural sciences, PhD in archaeological conservation and chemistry, and worked for 2 years in industrial ceramics research. He joined the British Museum in 1990, specializing in preventive conservation and in organic materials conservation research. He joined English Heritage in 2003 as senior conservation scientist, mainly researching preventive conservation. Recent projects have focused on historic house environments, pollution and damage, collections, demography and epidemiology, non destructive testing, microclimate frames, and optical coherence tomography. He is an assistant coordinator of the ICOMCC Metals Working Group and an ex coordinator of the Preventive Conservation Working Group. He sits as a UK expert to the European standard CE and TC 346 conservation standard and is a director and is a board member of the Indoor Air Quality and Infrared and Raman user groups. He has published over 100 research papers and co-supervised 6 PhDs so far. The topic for today's talk is preventive conservation of metals. Metals corrosion depends on RH, pollutant, gases, and particles. Different metals react to different factors more strongly. Understanding the exact requirements for objects allows much more targeted and effective preventive conservation. Copper alloys, steels, lead, and archaeological iron and copper alloys will be reviewed. Recent research has elucidated many elements of showcase performance and how to design new showcases and
Okay, so thank you for the invite to talk today. And today I'm going to talk about preventive conservation of metals, mainly indoors, mainly fine art metals, except from silver, which I talked about a few weeks ago, and apparently the video is on the YouTube channel if people would like to catch up with that. I'm going to cover quite a lot of material. But a lot of what I'm going to talk about is available on the World Wide Web, and I will show this at the end. But there's quite a lot of websites you can go to download these resources, but also to find out more. There's quite comprehensive instructions. So I'll just skip over the principles today without going into the detail. And as I say, I will show this slide at the end, and Padma's going to put my email address up in the chat. If anybody wants, what's got details of these, please feel very free to email me. I'm very happy to pass them on. Now, metals corrosion has been a problem for a very long time. First reported or written down about in ancient Greek times, and we get instances like this with corrosion of lead, the coin on your right, and a lead inlay on a Japanese lacquer box on your left. And one of the other two big metals I'm going to talk about is copper alloy, and here we see examples of acetate-based corrosion with the two left ones, this very bright blue corrosion, and we can see how disfiguring this is. And then a little more subtle, we have malachite corrosion on the image on the right-hand side. And today, I'm going to really talk about three areas. The first is the principles of corrosion. What are the factors that cause it? How we measure those factors, and then a little bit at the end about how we go about mitigating them. So the principal thing that causes corrosion, as I'm sure you're very aware, is high relative humidity. And if your relative humidity is less than about 40%, you'll see an incredibly slow corrosion rate. You probably will never actually be able to see it for everything except archaeological iron and copper. Between 40 and 70% corrosion speeds up, but it's still very slow and generally not a problem. And at some point over around 70%, corrosion becomes rapid and is an issue. And the actual humidity that occurs for a particular metal depends on the pollution in the environment around it and on its surface. And talking about pollution, the kind of things we're talking about are the things that are coming from the outside air, which I'm going to call external pollution through this. So that's nitrogen dioxide, sulfur dioxide, and ozone predominantly, and some dust particulate. And this is a map of the atmospheric sulfur dioxide above India. And then many metals are displayed in showcases, and we have a different suite of pollutants we need to worry about with those. There's quite a lot of them. Over 40 species have been reported to cause damage, but the big ones, the main ones that cause a lot of damage are acetic acid, formic acid, formaldehyde if you have very high relative humidities, a couple of sulfide gases, and then coming down to the less common ones, things like ethyl acetate and styrene. And you can see all of those gases can affect some metals there. Okay, so these charts show the effect of relative humidity on the corrosion rate of carbon steel. The one on the left, we have relative humidity along the bottom and some measure of corrosion rate up the side, and the different charts have different measures. But the one on the left is at very high levels of SO2, and these are the kind of levels you would find in industrial processes. You're not going to find them in the air normally, and that depresses the critical RH where it really speeds up down to about 60%, but more normally that would be around 70%. And a more normal situation, if you are near the sea, is steel in contact with particles, sea salt, and you can see there is corrosion at the lower levels, but at about 70, it's really beginning to speed up. Okay. Moving on to copper corrosion. Again, this is an amalgamated slide with research from several studies, but you can see it's relatively slow and it follows this curve and begins to speed up. And by 70%, it's beginning to get much faster. Okay, so we're going to consider pollution next, and these graphs are slightly different. So the bottom axis is the amount of the vapor that we're interested in this case, formic acid, and this is in ppm, and again, some measure of corrosion rate. And as you can see here, at 40%, even if we have very, very high levels of formic acid, the corrosion rate doesn't go up a great deal. It accelerates faster at 80% with the higher levels, and at 100%, it really is very fast. And I should say this, the numbers on this piece of work, 10 ppm, is very, very polluted. There are very few showcases that would have that level of formic acid in them, but there are a few. And then acetic acid, one of the other ones, a similar behavior, really very slow corrosion, almost zero at 40% here, increasing at 80 and much faster at 100%, as you perhaps expect. I'm afraid the crying you can hear is my cat, who is determined to have some attention. Okay, now a graph of the lower concentrations for acetic acid with copper. And one of the things that's quite important with this is we quite often see a threshold. So it's below certain levels, the corrosion rate is really not above what we can measure as a back zero. And then once you go beyond this level of pollution, the corrosion begins to get much faster. And that's a threshold level. And we can use it quite well within preventive conservation to say, well, if we keep the acetic acid concentration down below, and this one I would say it is about 1 or 2 parts per million of acetic acid, then we won't see corrosion. So that gives us a target to aim for in our showcases. And I should say these gases will only really build up in showcases or enclosures such as cupboards, drawers, etc. They're very, very rarely an issue in a room. Okay, moving on to lead. Again, This is acetic acid, similar behavior. We have a threshold. It's about zero 0.4 milligrams per meter cubed. And I'm afraid with pollution, there are two sets of ways of measuring it. One is milligrams or micrograms per meter cubed. The second is parts per billion or parts per million. And there's a simple mathematical transformation that you can find on the web. But for lead, below zero 0.4 milligrams per meter cubed, 400 micrograms per meter cubed, you really don't see any corrosion at anything but stupidly high relative humidities. And the other important behavior is at low relative humidity, such as 34%, you really don't see any acceleration in corrosion in quite high levels of acetic acid. So if you keep your situation dry, you won't see corrosion of lead, even if there's a lot of acetic acid. Okay, formic acid reacts a little bit differently with lead. There is a threshold, but it's much lower, and it's actually just probably beginning here on this chart. The data is not very good, but lead is more sensitive to formic acid than it is towards acetic acid. So that's just a very quick skip over RH and pollution, or gaseous pollution. The composition of the metal is very important as well. Iron and lead tend to be more susceptible, copper alloys tend to be more resistant, but the composition of the alloy can really dramatically alter the corrosion rates. You can have 1,000 times difference in response in a lead that is pure lead and one that has 2 or 3% zinc in it. It will corrode much, much more slowly. And I mentioned archaeological metals. For archaeological iron, if you look in the literature, there's a lot of research been done, there's a lot of papers published, and rather unhelpfully, if you read all of those papers, you will see a very different number of RH values quoted, that if you keep your archaeological iron below this value, it will be stable. And there's an enormous difference between 11% and 58%. We benefited from a lot of research in the last decade. There's been 4 PhDs, 2 large research projects, and I think we can now quite confidently say that for most archaeological iron, it follows this kind of profile. So below a certain RH value, 11 or 16%, depending what happened when it initially came out of the ground, there is no corrosion at all. Below 30%, the corrosion, the deterioration is extremely slow, and then it begins to speed up. And again, at about 50 to 55%, depending on the temperature, it speeds up dramatically. So if we're trying to keep archaeological iron safe, and we maybe can't afford to keep it below 16%, which is actually quite difficult and expensive to do, we can decide how much risk we're prepared to accept with that iron. At English Heritage, we tend to say we'll keep our showcases below 30%. We accept we'll get a very slow deterioration, but it's an economic thing with the resources that we don't have to keep it below 11%, whereas in storage, we do keep it below 11%. And if we, there's been a lot of work looking at whether this lab-based work translates into reality. Objects are very complex, their interaction with the environment is very complex. Archaeological objects are even more complex. And this is that same chart, but with the results of damage assessment of over 2,500 archaeological iron objects on display at different relative humidities, which is what the black spots are, and they do give quite a good agreement with this lab-based piece of work. So I think we can be reasonably confident that's a good model for most sites. Other researchers have worked in this field. This is work from Cardiff University, and they found a similar result with the green curve, and about 120 archaeological sites have been shown to fit onto this green curve. A single site shows the blue curve, so it's much stable at higher humidities, but if the humidity gets high enough, it corrodes. And the single site has been found to be much, much more reactive and corroding at much lower relative humidity, possibly because there's a lot more chloride in the soil at that site. So that covers the effect of relative humidity. We're now going to look at the effect of pollution. And because if we look at different RHs, at 30% there's a very low corrosion, at 50 we're already getting corrosion, at 75 we're getting a lot of corrosion. I've presented the graphs in a different way. So what I've done is I've run a series of experiments with tubes with just water vapor in them, relative humidity, and ones with, in this case, formic acid. And I took the amount of corrosion with the tube with just water vapor as 100%, and then calculated the increase in corrosion rate with the other species. And you can see with formic acid, there is a impact and increase, and it can almost triple the rate of corrosion at the higher concentrations. And I will say that for most situations in museums, this is the sort of level we're going to get. This is very rare, but it does occur. And the final point on the chart is for nitrogen dioxide and sulfur dioxide. These are the results after 3 months. This will be the equivalent of about 6 years exposure to the normal levels of nitrogen dioxide, sulfur dioxide in the air. So the formic acid has a much, much stronger effect. And then similar work with acetic acid and formaldehyde that seems to have the even strongest effect. And then similarly for archaeological copper, the RH response shows some similarities, very slow from about 23, 24%, a jump at about 35, and then it begins to increase much higher at higher RHs. And much less impact of acetic acid there. The previous graphs were up to 3 times. This is just a 5% increase with even higher concentrations. Formic acid slightly higher impact at 75%, but still much weaker than with archaeological iron. So that's just a quick skip through the kind of information we could use if we take some measurements to assess how much risk we have to particular types of metal objects. And another thing that we need to worry about is dust. These are steel coupons put into a set of tunnels, and the RHs and gaseous pollution levels were about the same, but the one on the right had much more dust. And you can see there is quite clearly much more corrosion on this. If you look under a microscope, and I'm going to show an example from silver here because I have some nice pictures, at the early stages of corrosion on tarnish, you quite often see these effects around dust particles. So if this is a dust particle, you can see the banding of sulfide tarnish, different kind of dust particle. This one's calcite. You can see the band of white silver oxide forming around that particle. And we've done quite a lot of work looking at the exact impact of dust in English heritage's environment. It's one of the research areas I'm interested in. We know for us, the main things for preventive conservation factors, but actually what's the detail? How much of an impact does dust have? How much of an impact does a certain level of acetic acid have? And these are results where we took a series of metal coupons, some of them at 45 degrees and some of them held horizontally, but about 6 centimeters above the surface. So the underside of the coupon has access to air. It has the same relative humidity, the same pollutant gas level, but it's receiving much less dust falling on its surface. It does receive some dust, but it's maybe 5%, 2% of what's falling on the top surface. Then after a period of exposure, we analyze how much corrosion is on that surface. And this is the ratio. So the green line is drawn at 1 if the bottom surface was the same as the top. And you can see in some rooms we're getting 10 times as much corrosion on the top surface as the bottom surface. So that we can put down to dust. So the dust is having really a very dramatic effect in that particular environment. And you'll notice some of the points we don't have that. Apsley case, Rangers case, so it's inside showcases that doesn't happen. And the Apsley Waterloo Gallery has has a air conditioning and a dust filtration system in it, and that is stopping that process again. This is for silver. We get very similar results for copper, very high levels, except where we're in showcases. And we've only measured results for steel in rooms, not in the showcases as such. But again, with steel, we're seeing big increases due to the dust. So as we can certainly say dust has a impact. And if we look at the literature about damage from dust, it's this top point that really, I think, is affecting metal corrosion, but dust can affect a wide range of other materials as well. And dust comes from a lot of different sources. And because it comes from different sources, it's quite different in different places around the world. A molecule of sulfur dioxide is the same in Delhi as it is in Beijing, as it is in London, whereas a particle of dust will probably be different in each place. So they're quite difficult things to measure. And the other thing is the different dust particles have very different diameters, which makes measurement difficult, but also changes their behavior. Essentially, the large particles tend to stay low down near the ground. They only stay in the air a short time before falling out. They don't penetrate into cracks and gaps. Smaller particles around 1 micron and below stay in the air a long time. They don't tend to deposit, and they will go through very fine cracks and gaps. So they'll find their way into showcases. They'll find their way through closed windows in a way large particles won't. Little piece of work from India, actually. Some of the dust is very seasonal, and the monsoon tends to wash coarse dust like soil dust out of the air. And you can see here there's much less dust depositing during the monsoon months than the rest of the year. Okay, so that's what we know. I'm just showing this slide. I don't expect you to look at the detail, but essentially what I said is if we had all of the measurements we wanted, we've measured our relative humidity, we've measured all the pollutant gases we wanted, we've measured the dust, could we assess if a particular metal was at risk with those measurements, with the information we have at the moment? And I've color coded this green as yes, red as no, we definitely would have some gaps, and yellow, we might be able to have a go, but we'd probably find some problems. And really, the thing to take away from the slide is that there's not so much green on there. There's a lot we still need to find out about metal corrosion for our particular metals if we're going to be able to manage this properly. Okay, so I'm now going to move on to measuring. We know what things are. We know what things are. We know what the things are we are looking at, but we need to measure them to be able to assess if there's a problem. And there's a very wide range of different techniques we can use. I'm showing some pictures here and another set here. Really, all I'm going to talk about today are the more accessible, lower cost techniques, but there are many more. And I actually ran a course on this earlier in the year in America, a full one-day course on all the different measurements that you can take. But looking at the more accessible techniques, it's worth bearing in mind that we monitor for different reasons. We may be moving a collection into a space. We want to know if things are generally okay. We may have observed corrosion and be trying to figure out what went wrong, why it happened. We may be doing a risk assessment. Any of the first three may have told us that there is a problem. We're trying to mitigate the damage, and we need to check that mitigation has worked, whatever we've changed. And we also sometimes do long-term monitoring. So just looking at the techniques, There were a number of coloured test papers that you can use. This is one for ozone, so as we could use it for ozone in air. You just put one of the strips out, look at the colour change after a period with your eye, and match it to the scale on the side. For internal pollutants, we've done a lot of work with what are called AD strips. They're a pH indicator. They were designed for putting into cinefilm canisters because the cellulose acetate degrades to give acetic acid. They come with a colour scale and a neat pencil, but the levels here are much higher than we'd find in almost any showcases. So we developed our own colour scale. If you happen to have access to an instrument called a colorimeter, then you can do some kind of quantification. You can measure that change in colour with the machine, run it on a calibration graph, and you can get some idea in terms of an equivalent acetic acid concentration in micrograms per meter cubed. If you don't have access to that kind of equipment, just before the pandemic, we were looking at developing our own guide charts for these, and that's what this is. This is the colour of the strip. If you put it beside the guide chart, you'll be able to read it into these kind of divisions. The pandemic kind of stopped this work. We hope to pick it up again soon and be able to provide people with the colour coordinates so they can print their own charts should they want to. There are all of these things that I've shown you. There are drawbacks with them. The AD strips seem to respond to the environment an average of the last 3 days. If you put them in a showcase and take them out, you need to read them very quickly. They'll start to change after 5 minutes. And there's a degree of light sensitivity. So if you put them in a very bright space, you'll break down the dye before it reacts. Okay. They were just beginning to come onto the market, these little kind of things for measuring NO2 and ozone. They're about, I think this one is about $30. Its sensitivity is quite poor. It's about 10 to 20 ppb. It will tell you if you've got a major problem, but it won't read anything in levels that can still be a problem for what we're interested in. And previously, we've used these very large mains powered units that are very sensitive but incredibly expensive. And recently, there's something come onto the market that will read at the sort of level we want, but it's still about $1,000. So it's not something that a large number of people are going to start using. Whereas these may be, and as I say, they're perfectly good for telling you you've got a major problem, but they're not sensitive enough for a lot of the monitoring we're trying to do. And just with those gas sensors, the choice is a species is very limited at the moment. As you saw, you need to pay quite a bit for the sufficient accuracy. Okay, I'm just going to talk about a kit that was developed by the National Trust. We had a little bit to do with developing this, and you can download a 60-page booklet about it. It uses sticky samplers, the kind of magnifiers you'd use for insect pest management, or if you've got it, a microscope, and has some things to help you get the numbers out of what you're seeing and interpret them. And if you've got a microscope, to be able to identify the dust sources, and to buy the basic parts of it would cost you about $30. And as I say, the link is in that list that I showed you. So this is it's just a self-adhesive label in an old-fashioned slide holder. You put it out, collect the dust, and then look at it under a graticule, and it gives you lots of little images like this to estimate that this is between 2 and 5% coverage of the surface. And if you have a microscope, there's about 40 pages of different kinds of dust and what they look like for you to be able to tell where the dust is coming, and maybe give you some ideas about what you can do to stop that dust. And there is a grayscale with a different way of measuring, but I'm not going to talk about that in detail. But The details are all in that booklet if you're interested. As with pollution, there are lots of different ways of measuring the dust, and the one we're looking at is the dust kit. And you can use more and more expensive equipment or some quite expensive analytical equipment here. And if I put the sensitivity to particle size for the different techniques against that slide I showed you earlier, you can see they all will analyze different types of dust. And the dust kit is very accessible, but it will only analyze this coarser dust. There are other dusts that may be causing you problems that you won't be able to get with this quite simple analysis. Okay, another thing that is really very useful is just putting out metal coupons. And I've used the silver coupons as an example because there's some good pictures. So we can just put those out flat or in a rack. This is the 45-degree rack we use for the dust experiments. And you can just put them out for a period of time, bring them out and see how corroded they are. And the series of images on the top left are coupons from showcases in a single gallery that have been there for 2 years. And you can see some of the showcases, the silver is very tarnished, others it's still quite clean. So it's telling us a lot about performance. If we want to look at the impact of dust, again, we can make this simple rack and just look at the top and bottom of the coupon and compare it. We can do more analysis if we've got access to equipment to analyze the corrosion, how much it is, what the type is, but you need access to the equipment. We can do a similar thing with lead that goes from a grey like this to show white powder. And the issues with this really is looking at it by eye is a bit subjective. If I look at it and if one of you looks at it, you may think the levels of corrosion are different. It's relatively slow. If you've got a real problem, you might get a reaction within a week, but you're probably going to have to leave it a month or 2 months and ideally a year to really be sure about the numbers. We can do some other things like colorimetry, and again, I ran a course on this on the silver to give you a much more precise method. And things like orientation can affect it, but it also affects our objects. So that's not necessarily a big issue. And the big drawback with certainly using lead coupons is they won't react at low relative humidities. So as if your showcase is at about 30%, if it's very dry, there can be a lot of acetic acid in there and the lead won't react. Lead objects won't react, but other objects don't have the same RH response, and maybe they will react even though your lead doesn't show corrosion. Okay, we're going to talk a little bit about showcases now. And if we look at the kind of things we normally worry about in preventive conservation, the things on the left in blue, showcases will reduce, and if they're well designed, will reduce a lot. The things in grey at the bottom, the showcase will make no difference to, but the things in red can be much worse in a showcase. So we can build up these internal pollutions from the materials the showcase is made of, or sometimes from the objects themselves, and they tend to generate higher temperatures. So they'll generate a higher temperature than if the object was sat in the room, and the fluctuation in temperature will be higher as well. But the biggest problem with showcases is this internal pollution. And if we're worried about showcases, the thing that tells us a lot about this is the so-called air exchange rate. It's the amount of air moving in or out of the showcase. It's an intrinsic property of each showcase, and we normally express it in air changes per day. And the thing is, if we measure that, we can see a lot of the things we're worried about, interested in, do depend on it. So as the amount of dust getting into our showcase drops as the air exchange rate drops, the silver tarnish rate drops. I talked about this a lot more in my talk before. If we're trying to control relative humidity to a certain range here, 40 to 60% with silica gel, if the air exchange rate is 1 or below and the air exchange rate's along the bottom, that works. It keeps it within that range 100% of the time. As the air exchange rates get higher, 1.4, 2.6, the amount of time it spends in that band decreases. So it's controlling relative humidity is more difficult. And finally, this build-up of pollution, the bottom right here, in a set of very identical showcases, same amount of material, same material in them. As the air exchange, if the air exchange rate is quite high, 1.5 and 2, the pollution level is low acetic acid. As the air exchange rate drops, the pollution level builds up and really much higher at low air exchange rates. So we're exacerbating the problem. It's a very important parameter. Usually, if there's a high air exchange rate, moisture and pollutant from the outside will get in. So we tend to want low air exchange rates, but it can build up pollution inside. We'll talk a little bit about that later on. If we know the air exchange rate, we can predict a lot of things. So this is the top left here. The dark blue line is the room RH, the pale blue line is the measured room RH, the white line is a prediction knowing the air exchange rate. And you can see it's fairly close. If we want to keep showcases dry, this top left, this is one of our typical damp horrible castles. If we want to keep the RH low in a showcase by adding silica gel, we can predict how the showcase RH will change from putting very dry silica gel in. There, bottom left is how much a dehumidifier machine would need to work to keep an RH below a certain level. And the right-hand side is what will happen with showcases of decreasing air exchange rate for the ingress of sulfur dioxide, nitrogen dioxide, and ozone at different temperatures. And if we had an object, a piece of metal that we wanted to keep below say 5 ppb of sulfur dioxide, we can see that we need to keep the air exchange rate in this instance below about 1.2. So we can use this to say what we want our showcases to be able to achieve. Measuring this, we tend to do with carbon dioxide. We squirt some carbon dioxide into the showcase, normally out of the 2 little cylinders you see here. And we have a logger sitting here that measures the carbon dioxide. We leave it for a few days, the level drops, and we can use that to determine the air exchange rate. The loggers we use are quite expensive. They're about $1,000 because we measure rooms and other things with them. You could certainly get away with a $300 logger doing that. There are even more accessible ones. There was a summer school in the States last year where the students built their own carbon dioxide loggers for about $40 each using very widely available components. And they would measure to plus or minus 50 ppm, which is certainly good enough for what we're doing. As you can see, they're quite big boxes. So when we do the measurement, we measure the carbon dioxide in ppm against time, and we see the decay. And if we plot that mathematically slightly differently, there's a couple of papers that show you how to do this, we'll get a straight line, and the slope of that line is simply the air exchange rate that we're interested in. And showcases have very different air exchange rates. I've been measuring them for 20 years now. I've measured probably 2,500, 3,000 air exchange rates. I still can't look at a showcase and say whether it's going to be good. Some of them, if they've got big gaps, if you can see them with the naked eye, they're probably going to be bad. But most of the gaps we're looking at are so small, you can't see them with your eye. So you just have to do the measurement. And 2 showcases that look very similar, made by the same people, same time, can have quite different air exchange rates. A little bit about showcase design. Water vapor moves into a showcase in 3 main ways. If you imagine a typical showcase, so this is a sheet of glass or perspex, and maybe there's a wood or a metal frame it's sitting in, we have permeation through those materials, and glass and metal don't let the gas through. Wood lets it through to a degree, medium density fiberboard more so. Perspex lets a lot of moisture vapor through, polycarbonate is better. We'll always have gaps, no matter who builds it, how expensive it is, there will be gaps. They're hopefully very small, and we have a process of diffusion moving the gases in and out. But that's relatively slow. What really drives air exchange rate is what's called infiltration. If there's a pressure difference, and the pressure in the air always changes, so there will be, air will be blown through these gaps and it will take water molecules and pollution with it. And what really drives that is when we have two horizontal gaps that are separated vertically, which is pretty much any door anybody's ever built in a showcase, and we have something called the stack effect that really drives air exchange rate. So if you are involved in building showcases, lower cases will tend to have a lower air exchange rate. Desktop type cases tend to have a lower air exchange rate. And if you can build a 5-sided glass box just hinged at the bottom, that'll have a lower air exchange rate. As cases get deeper, they tend to have a lower air exchange rate. So things like print frames tend to be more leaky than shallow cases, tend to be more leaky than deep cases. Hinged doors often drop and tend to leak, so what's called pull and slide is better. If you're going to try and control the RH in a showcase, you want a low air exchange rate, lots of space for silica gel. Ideally, you want to change it without having to open the case up to the objects, and you need to have good size holes between wherever you put the silica gel and where the objects are. If you're using fiber optic lighting, you'll have lots of holes in the showcase for the fibers to come in. They need to be sealed. And when you put a showcase in a room, if it's in direct sunlight, even if you've got double blinds, you will find problems with heating and lighting, and things like computers generate heat as well. Okay. One of the things that we're able to do, and this is available online, is if you want to keep showcases dry for silica gel, we can do this kind of modeling. So if you put a year's worth of if you've got a year's worth of art-based data you can put in, or you can estimate a year's worth of data, you know how dry the gel will to begin. If you know how much of the gel there is, kilograms per meter cubed, and the air exchange rate, you can feed it into an Excel spreadsheet and it will predict how long it will take to get above a certain value. As I said, for archaeological iron, we use 30%. So as we can see here at this point, we need to change and refresh the gel. And that's written up in the reference at the bottom. As I say, it's an Excel file. It's available online. There are instructions online as well, and the link I will show you at the end. Okay. Internal pollutants we've talked about. Where are they coming from? They're coming from materials, and this is what they're affecting. We've seen these are the materials that they're coming from. Wood and wood products are always a problem or can be a problem for many metals in showcases. The best thing to avoid this is a thing called the oddity test, which is just a matter of putting 3 metals in a glass tube with a sample of the material, some water to keep it damp, and run it at 60 degrees C for 4 weeks. If you don't see corrosion on those metals, you will never see corrosion with that material in a showcase. There were lots of results online for that. And the final bit I'm going to talk about is mitigation. We've got a very large online tool that we developed, about 600 pages. The link's at the end, but I always just search Memoria Nilu and it will take you straight into it. Amongst the other things in there, there is a collation of all the data we have about acetic acid, formic acid, nitrogen dioxide, and ozone effects on objects. And each one of these, if you click on them, will take you to a load of information. You'll get a chart like this, which is for damage to lead, and it shows you the risk level at different levels of formic acid, acetic acid, nitrogen dioxide, ozone. It's green if we don't think you'll get any corrosion within 30 years or noticeable corrosion. It's red if we think you'll get noticeable corrosion within 2 years, and it's yellow if we think it's somewhere in between. There's also a lot of information about, what pollutant levels, what does the damage look like, and other things affecting deterioration, like composition. And we recently updated this to put the effects of relative humidity. So this chart's at 54%. If we clicked on 30, these bars would perhaps move up and down. There's a lot in that tool about mitigation. Because it's written in the tool, I'm not going to talk a great deal about it. But basically, there's a hierarchy of doing things. The best thing to do is to avoid bad materials, oddity testing, or something similar. If you can't avoid them, block them. And this is my colleague Paul Lancaster putting aluminium film over MDF boards. If you can't block them, dilute them. Either have some holes in the showcase or put a fan in the showcase. There are problems with that, with dust and external pollution. If that doesn't work, put an absorbent in, like activated charcoal cloth. If that doesn't work, put it in a filter. But as I say, the website has lots of pages on how to do that and when it's likely to work and not. There's a number of other models. This is the dilution model. So as if we change the air exchange rate, what are the pollutant levels likely to look like? So if we went from 1 to 10, we'd see a reduction of about 80% in pollution for acetic acid in this instance. And then I'm just going to finish off with a few words on dust mitigation. The earlier work shows dust has a big impact on corrosion. That's something we need to worry about, but it also opens up another set of ways that we could slow down corrosion. Because particularly on open display in a room, it's quite expensive to control relative humidity. It's quite expensive to filter pollutants out. Dust we can deal with in lower tech methods. We can make sure the doors and windows are closed as much as possible. We can ensure the floors are cleaned regularly. If the floors are cleaned daily, or maybe less frequently, but in a way that the dust isn't just moved around, it will stop dust deposition on objects quite dramatically. And there are things we can do with positioning, perhaps in a room, putting objects on plinths, and I'm not going to talk about the mechanical filters and ventilation today. But this is a series of dust measurements in a room where the public are kept behind a barrier in this area. And you can see the dust levels much higher here, and it drops off as far as we get from the barrier. So as if you're using this kind of thing, and if you've got a choice about where you put your object, try and put it as far away from people, the barrier, possible. If we look at the vertical distribution of dust, there's a lot of dust that moves very close to the floor, and that's usually quite coarse dust. It drops off generally the higher you get, and there's another peak around 1 meter, and this is because of the way that people move, and when they move their bodies, they emit all sorts of fibers, etc. But what this means is if you can put your object on a plinth, if you can keep it 20 centimeters above the floor, you'll cut out a lot of this floorborne dust. So that would be really beneficial for something that's not a big change. And then finally, if you have a tour route, this is a historic house, people are kept in this area behind the stanchions. At the beginning of the tour route, or the rooms that people first come into, they'll be much more energetic and you'll get much more dust deposition. By the time they've walked through 5 or 10 or 15 rooms, the amount of dust will reduce. And for the tour route, where they tend to have to go around corners or bends, you get higher levels of dust than straight. So perhaps you're able to influence how these kind of things work. Okay, so we covered an awful lot there, and I just want to finish with some acknowledgements to people involved in the Memorial project that produced the tool that's online. Marianne Odlier, Stephen Hackney, Catherine Hallett, LTEC, and Memorial was funded by the European Union. And I will just finish with all of the downloads if anybody wants it.
Thank you, David. I'm sorry, I lost my connection for a bit there, and you have to start without a proper introduction. My apologies for that. But I don't see any questions.
Nice.
I think that's very nice. Please type in your questions, everyone. But I have one question. Usually, in the museums and showcases, we normally rely on the color change of silica gel. I mean, that's I think a very common thing that happens in most of our museums in India, if I can say, and that's what I know. So just to, with the, you have monitored and you have measurements, how far away would it be for someone if he changes when he sees the color change? Uh,
Okay.
it means we've lost a lot of time by the time the color changes, or is there some sort of,
Okay.
yeah.
Yes. So most silica gels change around 30 to 40%. And many of them are driven by actually a military specification for shipping military equipment around the world, which says they have to change at 30%. So for a lot of things, that's fine. If, as I said, for our showcases with the most R8 sensitive material, archaeological iron, we say we should keep it below 30%, so the colour gel change should be okay. There's been some research that's shown that for particular types of gel, that range can be a bit wider. So you might be getting a bit higher, but it's probably okay. You can also get color indicator cards, the cards with little colored circles on. Generally, they run in like 10% intervals. You can get, if you're worried about this for something that's very sensitive, you can get ones that run just up to 30% RH and run in 5% intervals, and they're fine. They're much better if you're trying to keep it below 30 on that. But for non-archaeological metals, the indicator is absolutely fine.
Okay, thank you. We have a question. Do you have any information about the relative rates of corrosion of mild steel and traditional wrought iron? The particulate iron.
Yes. Right. The first thing to say is that traditional wrought iron is very variable. So there have been some measurements, and actually, certainly for some of the traditional wrought iron, it's not that dissimilar from mild steel. People often use a low carbon mild steel as if they can't get wrought iron experimentally. But as I say, the wrought iron will have quite a range of different values because it's been made in slightly different ways with slightly different impurities. But as an overview, you could say they're sort of similar.
Okay. But there is information available about the relative rates of corrosion.
Yeah, there's two or three papers.
Maybe
if you want to email me, I'm very happy to.
Okay, maybe Jeff can email you and then get that information. So no questions. So I'll ask the last question that I had in mind. You talked about the air circulation. It should be low. The air exchange rate should be low. So if I'm looking at a showcase, is there any way once the showcase is there to kind of control that? Or after it's been,
Absolutely. We've done a lot of work with older showcases where we've gone along, measured the air exchange rate, said it's too high, and tried to improve it. You can do things like generally making sure the showcase is level often has a big impact. So as if you're able to kind of make sure it sits flat, you can change all of the compression seals. There's usually little felt seals or plastic seals. If you replace all of those, wooden showcases, the wood can warp with time. And the best way to do that is if you're able to cut a slot in the wood and have it so the seal sits into a slot. We've done that, but there are a number of ways of doing it. And I actually published a paper
in the ICOM-CC proceedings in Delhi in 2008 about refitting old showcases, because it is possible. It just takes a little bit of work, and if you do it, it's important to have some way of assessing how well it's worked. You know, ideally have some measurement before and then afterwards.
So, for complete sealing, is that what you're saying?
It depends what's in the showcase and what. It's what's in the showcase, what it needs, what the room is it's in, how much work the showcase has got to do. But if it's got to do a lot of work, the more tightly sealed, the better. You just need to be very careful about showcase materials, because the more tightly sealed, you may cause problems that you wouldn't if it was a bit leaky.
Okay, I think we don't have any more questions. Thank you, David. Thank you so much for that presentation. I think we all enjoyed a lot of technical statistics and a lot of information. And everyone, please, those are the linkages. If you can note them down, the links to various sites, the slide is there. So hopefully everybody must have noted those down. So,
yeah, and as I say, if anybody wants to email me for any of them, I'm very happy to.
Yeah, your email address is also there right on top. david.org.uk. So it's there. So hopefully you'll get a lot of requests and further queries. So thank you, David, for doing this talk. It was a pleasure again. Thank you, everyone, for joining us. It's always nice to have a nice audience, and because there were not many questions, I'm assuming everybody enjoyed it and understood completely. So thank you. See you then.
Bye, everybody. Thank you.
I have a request, David, a small request. Is it possible for you to send me the first few slides of your presentation, because the recording did miss out because I lost the connection. So few slides would have slipped in your presentation.
So, yeah, sure. I'll try and send you the whole thing, Padma.
Yeah, I'll just insert those so that, there's a little completion, although I think only a few minutes were lost. Thank you. Great. Thank you so much. Bye. Take care. Bye. Everyone. Bye.